Greetings. My name is Bill Scamrock, and in this presentation we're going to have an overview of the transport schemes available in MPAS-Atmosphere. And we're going to focus on the horizontal flux divergence operators, the horizontal transport schemes, because those are of most interest and the ones that people are probably least familiar with, given the unstructured Voronoi mesh that MPAS uses. We're also going to look at dissipation operators because they're cast in terms of a turbulent transport or a turbulence flux divergence. We'll look at the nameless parameters that are used to set both the explicit resolved transport options and the turbulence options. And then I'll provide a few references for those of you who might be interested in looking more at the theory and the results that go behind the formulations that we're going to talk about today. MPAS is built upon an unstructured centroidal Voronoi mesh that we use on the sphere, although we also have the capability of simulating on a Cartesian planes. And that mesh is depicted in the left side of the slide here. What distinguishes this mesh and the properties we take advantage of is the fact that the cell centers are the center of mass of the mesh, and the lines connecting the cell centers here, A to B, are bisected by the cell edges and are perpendicular to the edges. And it is fluxes across these edges that we're going to compute as part of these transport schemes in the MPAS-Atmosphere formulations. So we take advantage of the fact that the normal velocity is prognosed here. We solve for the normal velocity here. Let's consider the velocity, an average velocity along the cell edges, and it allows us to compute these fluxes with the transport schemes that you'll see that we employ in MPAS-A. MPAS uses a C-grid staggering, meaning that the velocities are prognosed. The velocities we solve for are located on the cell edges and perpendicular to those cell edges. And the uniform resolution mesh that we use is the typical icosahedral mesh that perhaps some of you are familiar with that are used in other models, although we have this unstructured Voronoi mesh that allows us to use variable resolution and generate meshes that satisfy the distribution of cell spacing and mesh cell density that we wish. There are effectively a number of places within the equations that are where we apply transport or flux divergence operators. And there are two places I want to draw attention to. One is associated with the dry air flux divergence. So this equation here for the density of dry air, and the tilde denotes multiplication by vertical metric. It essentially states that the dry air is conserved, there's no sources of sinks here, and it has this mass divergence in the equation that we have to evaluate. This term here, this flux divergence of the dry air mass, also shows up in the horizontal momentum equation in the way we've cast it. And essentially, we solve for the horizontal momentum. This is the density times the velocity at that cell face that we solve for. And this is a piece we pick up when transforming the horizontal momentum equation from a vective form for just the velocity to the momentum, the density times the velocity. So we're going to look at how we do the dry air flux divergence first, and then we'll look at how we do the other flux divergences. But first, how do we go from essentially a time rate of change of a quantity and its flux divergence? How do we do the basic discretization? We begin with a canonical equation for some scalar C right here, and we say that the time rate of change of that scalar is equal to minus its flux divergence. In the finite volume formulation that MPAS-Atmosphere uses, we integrate these equations over the cell. And here I'm showing a two-dimensional depiction of that cell. So we perform an integral over that cell, and that gives us the equation, this third equation here, where the time rate of change of the average the mass in the cell, and this over bar, it denotes a volume integral or an area integral in the 2D case over the cell is equal to the integral over the cell here, which has been transformed using the divergence theorem to give you an integral of fluxes into and out of the cell over its boundaries, in this case over its edges. And we discretize in time and space to the mass, the new mass in the cell is equal to the old mass in the cell minus the summation of the time and space to average integral of the flux through the cell edges. The thing to note here is that this equation is still exact. Where the approximations come in is right here, how we do the time-space integral over the cell edges of fluxes into and out of the cell. That's where the approximations come in. And as you see here, D is the distance, the length of the cell edge, or it could be the area of a cell face for a three-dimensional volume, as we'll see in a short while. This here is the flux. It's the density times the velocity times the mixing ratio here. Now, this quantity here, the mass flux through the cell space, is usually given to a traditional transport scheme. It has the mass flux as a starting point, and then what it needs to do is determine what the appropriate value of that mixing ratio should be at the cell face. And that's just, that's the level of approximation that we use in defining our transport schemes. So first, let's look at this dry air mass flux divergence here. This term shows up in two places. Now note, this capital V is the density times the velocity. That's as depicted down here. The bold-faced capital V is normal velocity times the density defined at the cell edge. And for these mass flux divergences, we just take the average of the two densities from the cells that share that edge. And that's depicted here in this figure. Here's the velocity we're predicting in red. Here are the densities, in this case, rho underscore 1, rho underscore 0, that's used to define the velocity on the edge. And that's what we use for the velocities for the mass fluxes that we integrate around the cells in these formulations. An important aspect here is that we define this mass flux on the edge, and in the update equation for each of the cells, that mass flux is the same. So any mass flowing out of one cell flows into the other, and it's accounted for. So we conserve mass in that way. So that's the simplest thing we can do. We do this for the density because the density is always very smooth. If you look at output of density and you do contour plots on it, it tends to be a very smooth quantity, and going to more accurate transport schemes, it's just not worth the cost or the effort to go to implementations of more accurate transport schemes in this case. Now next, let's look at these other flux divergences involving either, in this case, the horizontal momentum, or our prognostic potential temperature here, or any other scalar in which we're solving for. This QJ could be anything from water vapor to other precipitable or other water species, ice, snow, rain, grapple. It could be a mixing ratio for chemical species, for aerosols. It could be a number concentration, a higher moment of a quantity in another scheme. So this Q is meant to be almost anything. In some applications, for example, chemistry, you may have 200 to 300 constituents. You have many hundreds of constituents that are being integrated using this equation with sources and sinks that come from chemistry. So this is an important equation to consider, and it's essentially the integration of this equation and the thermodynamic equation that guide our choice of more accurate schemes for transport that you'll see, in this case for the horizontal component in particular. For those of you familiar with models that are constructed on a regular orthogonal global mesh, or regional mesh for that model, atmosphere models, take for example WRF, usually a flux at an interface is defined, for example, in WRF as the equation you see below. It's essentially, it's got a velocity or a mass flux here, defined here, and then it's got a formula to take these values of the mixing ratios and project them onto the cell face. In this case, it's got a component that's an average of these two, of the two cells near the face, and that would be the second order approximation we use for the density when we do just the dry air mass flux divergence. But then it's got higher order terms that increase the accuracy, the spatial accuracy of that operator. In this case, it's got higher order discrete derivatives that it's summing or taking the difference of to give you third or fourth order schemes within WRF. So you have this global coordinate in which the values are defined along a coordinate direction, along a coordinate line, that you can apply this kind of formula to. Look at the MPAS mesh. Say, for example, we want to compute the flux divergence through this red edge here, defined in the center. As you can see, if we try to define the normal to that and extend it out to acquire values out a distance from the edge, you can see it doesn't fall along cell centers. The mesh is unstructured. It doesn't have that orthogonal global structure that we can rely upon to use these kinds of transport schemes. So going back to the formulation, which is depicted here, and this is just copied from 2 slides ago. Here's the WRF formulation. If we look at these derivatives in here, what we can do is we can replace these derivatives by their continuous counterparts and write the equation as so. And then the approximation, the discrete approximation, comes down to a method to compute these discrete second derivatives that are in this direction here that the normal velocity is along this edge. So we need second derivatives for the mixing ratio at the cell centers phi1 and phi0, here and here, here and here, at these. We need approximations to those derivatives. Obviously, the average of phi1 and phi0 that make up the second order approximation doesn't require any further approximation. That's already there. But as we mentioned, it's not a very accurate scheme, and we want a more accurate scheme. So we move to defining these as continuous derivatives, and then we approximate these continuous derivatives using a least squares polynomial that we've computed, and then we take the derivative of that polynomial. Now, the reason that works so well, or that we can do that with an MPAS, is that, and efficiently, is that we can pre-compute the weights that make up that polynomial and that define those derivatives before the start of the integration and just store it. So we don't have to do a least squares fit every time we apply the operator. We have those weights already there. We have those weights to define the second derivative, and we're just all set to go based on that. So how does this work in more detail? If we look at the derivatives we want at psi 1 here, and these are denoted by these green underlined terms here, this is where we need that. We compute a least squares polynomial, taking into account these values here. In this case, there are 7 values. We've got a hexagon here, so there's 6 neighbors, so there's a center value and 6 neighbors. That's what we need to compute the derivatives for this piece here. And likewise, for the derivatives at size 0 here, the eye points here along that edge, we use these 7 values here as denoted by the blue circles to compute the blue underlying terms. So what we're left with is as follows. For just the second order operator, all you need is these 2 values. So these terms don't come into play, so that's the trivial case. For the third and fourth order schemes, you need to take into account not only the cells that share the edge, but all the neighbors of those 2 cells that share the edge to compute the approximations to the second derivatives in these 2 terms. These 2 are the same. One has a plus sign, one has a minus sign. For the third order scheme, meaning beta greater than 0, all these terms come into play. For the fourth order scheme, where beta is 0, only these 2 terms come into play, but you can see that the stencil is exactly the same. So there's not a significant savings to be had from when going from third to fourth order. And as you'll see in a moment, there are reasons why we prefer, and the default in MPAS is to use the third order scheme. Before we go into some examples and more generalization of the schemes, though, what we've done is we've shown you a discretization that allows us to project the mixing ratio onto the cell edge. We haven't talked anything about the time integration. And our time integration is a Runge-Kutta scheme for the scalar transport that's depicted in these equations below. And it's essentially a 3-step process where you step the solution forward to produce preliminary values. You reevaluate those flux divergence operators, those massive scalar flux operators, produce another predictor, another preliminary value, apply those operators again to then take the full time step. And you can show that this is a third order accurate scheme for scalar transport. As I mentioned, it takes into account all these cell values, not only the cells containing the edge, but all their neighbors. We need 3 evaluations of those flux divergence operators per Runge-Kutta time step. But this makes sense because essentially we're not doing a least squares evaluation, all the mechanics, all the operations involved in it. We can store off the weights beforehand. We don't need to know the mixing ratios before we apply it. So hence, it's quite efficient. So that's how we integrate in space and time our equations, our flux divergence operators for transport for scalars. What I've shown you is 2 dimensions. There are 3 dimensions in the MPAS mesh. It's a 3-dimensional atmosphere. So in addition to the horizontal edges, which we've talked about, there are 2 vertical faces. Now those have the area of the cell, and that's what we use here. So we also include the vertical fluxes. That leads us to the following equation, depicted here at the top for updating the scalar, where now we've included the vertical flux divergence and the number of faces that we need to compute the fluxes over are the horizontal faces of that hexagonal or maybe 5 or 7-sided cell, plus the 2 vertical faces. So you're multiplying the mass flux, which is computed using the formulas I showed you, or in the case of the vertical flux, it uses the same formulas as WRF because we do have an orthogonal continuous coordinate in the vertical. So we can use the old formulas in the vertical. We multiply that by now the area of the face through which that flux is valid, and we divide by the volume. If you go back and see the 2D formula, you can see we've just replaced edge lengths by areas and the cell area by the cell volume and added the 2 vertical fluxes. That's what we've done. So that is how that flux divergence is done. Now, There's one other aspect of the transport I want to point out. If you apply this scheme just as has been described, it can produce overshoots and undershoots of the mixing ratios. It can produce negative mass in a cell. So we have a method to address that, and that method is effectively a form of flux renormalization. And what that flux renormalization does is it decomposes the fluxes that we compute for all these phases into an upwind flux, which is just saying which way is the mass flux going. If it's going out of cell 0 into cell 1, we're just going to use the mixing ratio at cell 0 to define that times the mass flux is the upwind flux. And if the mass flux is into the cell, we use, in this case, the mixing ratio from the cell in which it's coming, So that's the upwind flux. And then we compute a correction, and that correction is just the difference between the full flux that we've computed using our full formula and the upwind flux. So that gives us the full flux. And we renormalize the higher order correction fluxes such that they are positive, definite, and monotonic, that they don't produce negatives, and that they don't produce any new maxima or minima. And that with that corrected flux, which we've denoted as R of the corrected flux, this function R, we just add that to the upwind flux to get the new flux and update the scalar mixing ratio in our scheme, the scalar mass. So this is the same thing that's done in WRF, as we do the same thing in MPAS. So this looks the same, and the procedures are the same. So let's look at some examples. And we're going to be looking at our horizontal flux divergence in a 2D problem. And what this 2D problem is, it's 2D flow on a sphere. And the flow is such that this is the solution here, and this is a concentration at the beginning and end time. So it goes from essentially 0 to 1,000. 1,000 in the middle, 0 out here, so it's this one circular region. And through the course of the integration, it gets stretched out in one direction, then the flow reverses and brings it back and unstretches it to give you this as the structure is propagating around the sphere. So there's a mean flow around plus a deformational flow, which stretches it out and brings it back to this shape here at the beginning and the end. And here's at the quarter time, and here's the 3/4 time to the full time rotating around the sphere and being deformed. If we look at solutions to that, here is our third order scheme, the solution on the far left, and you can see the effects of the deformation here. Although the solution is very symmetric about the center. That's a nice aspect of it. If you look at beta equals 0.5, so this is this upwinding term that produces some damping, and we use beta equals 1. So what we've done is reduce the amount of damping somewhat, and you can see that the amount that is stretched out from the exact solution, which is 2 of the contours are given by these thick black lines, it's stretched out a little bit less. If we go to beta equals 0.25 to reduce further the damping, we get a much closer to the exact solution in terms of the numerical solution. There's just a little bit of stretching, and you can see maybe a little bit of asymmetry creeping in. If we go to the fourth order scheme, beta equals 0, what you see is that we get a very accurate solution, but notice that there's quite a few asymmetries here and a little bit of raggedness in the solution here. So our default in MPAS is to use beta equals 0.25 in this formula for the horizontal flux divergences. This is a 2D test, so all you're seeing here is the horizontal flow, and this is one typical test of it. There's another flow that's very similar to what you just saw on the previous page, except The initial condition is two slotted cylinders. Here the maximum concentration is 1, the minimum concentration is 0 in the exact solution. They propagate around the sphere and are deformed, as you can see. So there's a flow that goes around the sphere and another one that deforms it horizontally in this interesting circular kind of shape. Here you're seeing where part of the where the slots in the cylinders affect the flow. On the top, you're seeing the basic scheme without the monotonic or positive definite limiter, without the renormalization. And you can see that there are undershoots here. There are values less than 0, and it turns out there may be a couple values greater than 0 right at some of these edges, greater than 1, I'm sorry, the original maximum value at these edges. There shouldn't be any values less than 0 or greater than 1 in the exact solution. That's known, that's part of the exact solution here. But you can see without the flux renormalization, we get a lot of noise out here from the dispersion errors of the scheme. With that flux renormalization that renders it monotonic, here are the solutions. They're not perfect. Of course, the initial conditions, these are slotted cylinders where the concentrations go from 1 to 0 across one cell length. So it is a discontinuity. These are discontinuous slotted cylinders on the mesh. Not going to be perfect. There are going to be some overshoots and undershoots, but as you can see, the solutions are very clean and very good looking, and all this waviness away from the significant parts of the solution where the significant concentration should be is gone. They're gone. And the costs you can also see if you look very closely, especially in the end times here. You can see that there's some dissipation. The maximum solution is definitely order maybe 0.9 to 0.95 instead of 1. So we've lost some amplitude here, but we've gained some nice physical aspects of the solution. It doesn't go below 0. It doesn't go above 1. Okay. You need to configure the transport. How do you do it? The default for the transport is the third order scheme, and you can configure that for the potential temperature theta, for scalars, or for the vertical momentum, W. Now, for the horizontal momentum, you can only choose a scheme order for the vertical advection. The horizontal terms, if you look at the discussion of the dynamics, the lecture in the dynamics, that's cast in vector invariant form, so there aren't any horizontal transport terms for the horizontal momentum. So you only can choose the order of the scheme for the vertical momentum. You can choose 2, 3, or 4, and you've seen on the previous slide what that implies for those. Default is 3. Our default is also a damping coefficient of 0.25, or that upwinding coefficient. That's what we've chosen, more or less based on the tests that you saw, but we also have done a lot of other tests looking at flow structures in fully three-dimensional simulations to verify that that is a reasonable choice. But you have access to that in the namelist.atmosphere, in the NHYD_model section of it. You can change these and experiment with them if you wish. The monotonic scheme is also on by default. That's true. You can turn that off if you wish. And this is where you'll find them in the namelist.atmosphere, in the default name list that you'll see when you build MPAS. It will be created, the default name list. And those will be the values in them. There are other operators in the Voronoi mesh that do accomplish transport, but that transport is part of the dissipation operator, so you can consider it a turbulent transport. So if we look at the transport scheme here, these are the terms in the transport equation. This is the resolved flux divergence that we discussed, that we described the transport scheme to. In the other terms, usually denoted by a capital letter, either F or R, these are source terms. These terms come from the physics, or we define them as physics. They're essentially either there's some turbulent transport scheme that gives you those fluxes, or you've got a term that you're using to apply dissipation in that equation, to apply diffusion, that looks like a flux divergence. It is a flux divergence. But in this case, the fluxing velocity is modeled based on turbulence theory or prescribed eddy viscosity or hyperviscosity. So for the second order scheme, the turbulent transport we define as a Smagorinsky scheme has a flux divergence that looks like so. Notice it's a positive sign. And the fluxing velocity, if you will, the turbulent velocity is the density times this K, the second order eddy viscosity. And typically, K is either prognosed through a particular formula, or you can set the K, the eddy viscosity, the second order eddy viscosity to be a constant. This can also be applied in the vertical. So this is meant to be three-dimensional. Likewise, we also have a turbulent flux that's a fourth order flux for horizontal transport in MPAS. So this is only a horizontal operator in MPAS, and that's where essentially we apply a second order del square, if you will, operator to the existing operator to come up with the fourth order operator. We move the fluxing velocity, if you will, this hyperviscosity times the density, to replace a turbulent velocity in this here, where now this is our operator for defining the mixing ratio on the cell phase. So this is just a fourth order hyperviscosity cast in terms of a turbulent flux. That's where this is. We have that in MPAS also. If you look at what that means in terms of discrete operators, this is the discrete operator we looked at previously. This is the discrete operator for the turbulent flux, the second order turbulent flux. Here is our turbulent velocity, our density times the eddy diffusivity. That's what that term is, these two here, times the gradient of the mixing ratio. That's a traditional turbulent flux formulation in a finite volume form. And what you see here is we've just taken this quantity here, this mixing ratio phi here, and we've applied this operator again to get you here. So if you look at this operator here, the second order operator, we've just repeated it down here, but we've pulled out the turbulent velocity and replaced it with this turbulent velocity out here. So this is the fourth order hyperviscosity formulation in MPAS. In MPAS, this is almost always a constant, whereas the second order operator, you can set this, you can set the turbulent velocity to be either a constant or you can diagnose it using the Smagorinsky formulation. The operators for dissipation that I've showed you on the previous slides, those apply to essentially all the variables that are cell-centered in the horizontal Voronoi mesh. The horizontal momentum, which also needs dissipation because there's energy and entropy cascades, and we need to have energy sinks for the high wave numbers, for the small wavelengths. We need to incorporate filters into that equation, but we don't have that flux divergence to fall back on, given that the horizontal velocity is defined at the cell faces and not the cell centers. So we put together our terms to put dissipation in the horizontal momentum equation in the classic sense, with the eddy viscosity as the outermost term and multiplying a Laplacian, a horizontal Laplacian, or for the higher order filters, a hyperviscosity multiplied by here del 4, essentially the del squared operator applied twice here. So it comes down to how do we discretize the Laplacian? The Laplacian for velocity can be broken up into two pieces. One is a horizontal derivative in the direction of that velocity of the velocity divergence. Here you see the blue circle here. That's that velocity divergence. That divergence is just essentially the velocities the normal velocity integrated around the edges, multiplied by the length times that velocity, for example, for each edge, summed, then divided by the area. It looks like a mass flux divergence, only in this case it's a velocity divergence, same thing. So it's defined at the cell centers, and that's where we want it, because we take the derivative in the direction of the velocity of that divergence. So here that is, divergence at A minus divergence at C to get this term for the Laplacian for this velocity in the red circle, this velocity at this cell face. The other component is the derivative along the cell face, so perpendicular to the velocity, of the vorticity eta. This is the vorticity, and the vorticity lives in the center of the triangles at the vertices. So it also is exactly where we want it. It is at the vertex, and we can take the derivative perpendicular to the velocity of that vorticity because it's defined there. This is how we define that horizontal vorticity, that horizontal operator for the second order filter. For the fourth order filter, we just take this operator twice and apply it. So it works as it should. No problem. And that is the filter for the horizontal momentum. There's one other aspect of this which I want to point out. Given now that it's the sum of two terms, we have, if we want, the capability or the choice to apply different either viscosities or hyperviscosities to the divergence term as opposed to the vorticity term in this formulation. In MPAS, we take advantage of that, as you'll see in the next couple of slides where we define, where we look at the nameless parameters, where we actually put a different weight on this term than on that term in applying the viscosities or the hyperviscosities. So, configuring the dissipation. There are a number of parameters you can set in the namelist.atmosphere where these coefficients are set. The first one to look at is which form of dissipation you want to use. The default is a 2D Smagorinsky. So for the second order filter, it uses the Smagorinsky's approach to compute the coefficient, and that essentially is that the second order eddy viscosities are proportional to the deformation of the flow. You can look in the literature or in the papers describing MPAS or almost any model, you'll find this formulation is used all over. You can also choose 2D fixed. If you choose to fix the viscosities, then the values you put into these parameters, these vis2 and vis4 parameters, are the ones that are going to be used for the viscosities in MPAS. These are physical viscosities, so they have units of meters squared per second or meters to the fourth per second in terms of the fourth order hyperviscosity. So you can specify those, and they will be held fixed throughout the whole mesh. If you've got a variable resolution and you set this scale with mesh equal to true, and that's the default, then these should be set to be the values that one would use on the finest portion of the mesh. So if you've got a 15 to 3 kilometer mesh, you would set these viscosities as you would on a 3 kilometer global mesh, and they will be scaled appropriately, that you would get a similar amount of filtering as you would if you used a scaled viscosity on the coarser meshes. Now, if you choose to use 2D Smagorinsky as default, there's also a parameter here, config length dissipation, and that should be set to the fine mesh length scale, or essentially the nominally smallest cell-centered distances on the fine mesh. So if you've got the 15 to 3 kilometer mesh, that should be 3,000 meters. If you've got a 60 to 15 kilometer mesh, that should be, as it's written here, 15,000 meters. The units of this are meters. and you need to set that. If you change meshes and you have a finer mesh than this and you forget to change it, oftentimes the model will go unstable because this value is used to set the fourth order background filter coefficient, to set that hyperviscosity that's used along with the Smagorinsky. And the hyperviscosity is set that it takes this length scale cubed times this coefficient here, the BIS4 2D Smagorinsky of 0.05. These are the default values. That sets the fourth order hyperviscosity. That gets you a hyperviscosity that typically is significantly less than what's used in climate models, but more attuned to what's used in a lot of NWP models. So just keep that in mind. MPAS uses as background filtering, and that's what that, in the hyperviscosity, that's how it's set. Finally, there's one more parameter I want to point out, this del4U div factor. This is used in the dissipation of the horizontal momentum for the second and fourth, or for the fourth order filter. That's where the 4 comes in here. It's only for the hyperviscosity, and that points out, or that sets this is the coefficient that multiplies the divergent component of that final application of the operator to get you to the fourth order hyperviscosity mixing for the horizontal momentum. So hence we're saying we're going to damp the divergence 10 times more than the vorticity component of the flow. And that's because the divergence in the flow is the part where the energy is cascading to when you get down to mesoscale and cloud scale resolutions, just scaling the hyperviscosity as you see here, it's just insufficient when we transition from an entropy cascade to the energy cascade that characterizes the mesoscale and cloud scale. So that is where that parameter is. You will not find this in the default namelist.atmosphere. You would need to add it as a hidden configuration parameter, but you can place it inside and set that value differently if you so choose. The references that you may want to look at, the first one here is a reference to the MPAS-Atmosphere model, the non-hydrostatic model, and that will give you an overview of much of what you've seen here. It won't go into great detail into a significant part of the discretization. If you want to know a lot more about the transport scheme, you can look at this paper here, the Skamrock and Gossman paper, and that will show you a derivation of the horizontal transport scheme that I presented in this talk, and it will also show you significantly more examples of how it performs and why we are using it.